Electrolytes versus non-electrolytes is what we're going to talk about first. And just real quickly, we've talked about this last semester. Electrolytes, of course, will conduct an electric current. And things that are electrolytes are going to be things that will ionize. And so your strong electrolytes, of course, are going to be things that strongly conduct a current, and that's going to be your aqueous solutions of ionic compounds. So like sodium chloride would be an example of that, because when sodium chloride breaks up, we talked about this on the last lesson. Well, you can't really see that negative sign, but there is a negative sign on chlorine. It separates into the two ions, and so that's what would conduct the electric current. Your strong acids will also completely dissociate, and these are a list of them, except one got left off, HClO3. Okay, so they will conduct electric current. And then your strong bases, and those are going to be ones that have hydroxide in it, and then it's group 1 and 2 bases, except beryllium. I just spelled except wrong. Beryllium and magnesium, they actually are weak bases, and they will not be strong. But if it is a weak acid or a weak base, it makes what's called a weak electrolyte. So it will very weakly conduct an electric current. And then your non-electrolytes are things that do not conduct electricity when they're either melted or in a solution. And those are going to be your covalent compounds and any organic molecules. So a very good example of a non-electrolyte is sugar. Sugar will not conduct an electric current. It'll dissolve, obviously. We've got sweet tea, we've got Kool-Aid, we've got drinks that are sweet, and so it will dissolve, but sugar is a non-electrolyte because it doesn't dissociate, and we talked about that earlier when we were talking about solvation, that it dissolves, but it does not break apart, so it doesn't conduct a current. So that's what this would look like. Difference between a strong, a weak, and a non is if I was trying to light a light bulb, the weak, of course, would be much dimmer than the strong, and then, of course, the non-electrolyte, nothing would happen. Okay?
So if electrolytes conduct electricity, should we not drink Gatorade and thunderstorms?
That's kind of a silly question. When they're talking about electrolytes, I mean, Gatorade would conduct an electric current, but when they're talking about electrolytes for your body, it's a little bit different. It's still going to conduct, like through the synapses and that sort of thing, but it's about your body's balance of like sodium and potassium, because if that gets out of balance, it can make you really sick. If it gets far enough out of balance, you can die, actually, from not having enough sodium or potassium, because there's certain mechanisms in your body that need those ions. So when people are talking about decreasing their sodium intake or increasing their sodium intake, they're not talking about sodium metal, because that's explosive in water. They're actually talking about the ion. So anytime you're talking about one of those, it's got to be an ion in your body. Pure sodium metal, you wouldn't consume it. But people just say sodium because they're talking about that. Okay? So the big bulk of our lesson today is concentration of solutions. Okay? There are several different types of concentration of solutions. Luckily for you gentlemen back there who are talking, that you only have to do molarity. Okay? In pre-AP we got to do percent and molality, but we're only going to do molarity. And this is the formula for molarity, which you need to fill in your notes. Okay? Molarity is going to be the number of moles of solute per liter of solution. And it's represented with the capital M. Okay? So whenever you see a problem and you see molarity, I want you to immediately think moles per liter. And that's how we usually shorten it. We just say moles per liter. But it's moles of solute. In other words, what's being dissolved in liters of solution, the entire solution. Okay? And because we're doing molarity with the liter on the bottom, all of our volumes need to be in liters. And remember, how many milliliters are in a liter? 1,000. So you'll be probably doing that conversion quite a bit, because quite honestly, most of the time when we measure volumes in the lab, we're measuring in milliliters. And so you'll have to convert that when we're doing a lot of these. So let's work an example. It says calculate the molarity of a solution prepared by dissolving 11.85 grams of potassium permanganate in enough water to make 250 milliliters. So first thing I see is I want to convert that to liters. So I would divide that by 1,000. You do not have to show this conversion because I mean most of you could probably do it in your head. I'm going to show you for the sake of people who are not sure. So it would be 0.75 liters. So if it's something with the 100 place right there, it's always going to be point that as a quick way to do it. So we're going to start with 11.85 grams of potassium permanganate, which is KMnO4. And remember, if I'm trying to get to molarity, it's moles per liter, and I'm in grams. So what am I going to have to do? I'm going to have to divide by the molar mass. So I got to convert to moles. So I've already added it up, so I will tell you that the molar mass of potassium permanganate is 158.04 grams per mole. Let's just write that down so someone doesn't ask, where did I get that number? Okay. So when I do that, I get that it's 0.075 moles. So my unit is moles per liter. So now I'm going to divide by the liters of solution in the problem, which we already converted to be 0.75 liters. So I'm going to divide by 0.75 liters, and then that gives me my answer. This one has 4, this one has 3, so I need 3 significant figures for my answer. So I'm going to get 0.100 molar KMnO4. So that's how you do that. So that's how you do it if you have straight out, like, this is what I need to do. I'm going to put that in there. It's going to tell me. But, yes?
Can you just do it in, like, one big formula?
You can. Yeah, like, if I was doing it on my own, I would do it in one big formula. Like, but I want y'all to see this step. But absolutely, you could do it as one big chain. Just know that when you get to this last step, it'd be 1 over 0.75. Because that's what you need to do. But, yeah, you can absolutely do it in one big step. But sometimes if I do it in one big step, people aren't sure. So for this part, I try to break it out. So these are going to be some molarity practice problems. I'm going to just make up right now on the spot. And so this is going to go on page 154 in your notebook. And so on this one, I want to calculate the mass that would be required. Okay, so let's say I want to, and this is something that actually I would have to do all the time whenever we're making up solutions in the lab. Let's say I'm making up a solution for us to do a lab on, and I calculate, okay, every group needs 10 milliliters, I got 10 groups per class. Yes?
Is it in the notes that?
No, this is going on page 154. These are extra examples. Yeah, this is going to be a left side. Oh, I'm in the wrong notebook. I'm sorry. Yeah, thanks for asking. Not page 154. I did the same thing yesterday, didn't I? Because I haven't filled out our notes, but I have pre-AP's examples, and so I am so sorry. It is going to be page 144. Sorry. All right. But anyway, so this is a calculation. Matter of fact, more oftentimes than not, I have to do this calculation because the lab says you need, let's say it says you need 0.250 molar of HCl, okay? And each class period is going to use maybe 100, 200 milliliters. So I said, okay, I'm just going to prepare 750 milliliters so it would last all day. So I want 750 milliliters of that, okay? And so I need to calculate the mass that I would need to add to it, okay? And actually that would be a liquid, so let's make this sodium chloride. Change that to sodium chloride. Because I wouldn't mass out HCl because it's an acid. So here's something that I need you to remember Okay? And I would write this down somewhere, that volume times molarity will equal number of moles of solute. Okay? Volume times molarity. So, I know I need to be in liters, so I'm going to start with 7.750 liters. I want to get rid of liters, so I'm going to put my molarity here. Because remember, big M means moles per liter. So now I have crossed out liters, and now I'm in moles, and how do I get from moles to grams? How do I get moles to grams, Hayden? You said it earlier.
Oh, molar mass.
Molar mass, yes. So I need to multiply by the molar mass. And so the molar mass of sodium chloride is 58.44 grams per mole. I hear some talking in the back. If you're not going to pay attention, at least don't talk and keep other people from paying attention. So I would multiply all that, and I would get that I need a molar mass, and I need, actually I need 2 sig figs right here because that's only got 2. So I would say that I needed, it comes out to be 10.96, so I would say 11 grams. And so I would go into the lab, I would get a mass of 11 grams of sodium chloride, and I would dissolve it into 750 milliliters of water. And when I did that, I would have a 0.25 molar solution. And then we could use that. Okay? So that's how you do it if you're calculating the mass. And that is on your worksheet today. Okay? That shows up on, I think, the last section. And then sometimes you might have to calculate volume. Okay? Sometimes you might have to calculate volume. So we're still going to use sodium chloride. Let's say that something was wrong with my balance, and I added 52 grams and it was a 0.83 molar solution, and I wanted to know what was my volume. What volume? Okay, could I make out of that to get? So I'm going to start a little bit differently. This time I'm going to say 52 grams of sodium chloride. I need to get to moles, so I'm going to divide by the molar mass. 58.44 grams per mole. Now I've gotten rid of grams, I want to get rid of moles. So I can divide by my molar my molarity. So 0.83 moles per liter. So I cross out moles. So I do 52 divided by 58.44 and the 0.83. And I would get 1.1 liters is how much that would form. Okay, so that's the way you do that. So you can use molarity as a conversion factor, and you will have to sometimes. And what the main thing is, when you see that big M, I want you to immediately think moles per liter. Okay? Does everybody have that? So that brings us to concentration of ions, which we don't actually have to do in here. So y'all can skip that. So skip. We don't do this. Y'all don't have that in your notes. That brings us to dilutions, but you do have to do that, and that's on your worksheet today too. Dilutions are very easy. We use this for concentrated, a lot of times we use it for concentrated acids. The M1, the big M is, what do you think? Molarity. And what do you think the big V is? Volume. Okay? So this side is molarity, and it's going to be the concentrated, which I'm going to abbreviate concentrated that way. The second molarity, M2, is molarity of the diluted solution. And of course, this is the initial volume, and this is the final. Okay? So does that formula look vaguely familiar? What does it remind you of?
Gas.
Gas laws. Yeah, it works just like Boyle's P1V1 because they're proportional to each other, so it works the same way when you rearrange it. Okay, so this one example says, how would you prepare 485 milliliters of 0.39 molar solution? Okay, these are going to be the M2 and the V2 because your M1 will always be bigger. And so since this is the bigger solution, this is going to be M1. Because your concentrated solution's always going to have a higher molarity. So that kind of makes it a little bit easier to distinguish which is which. Okay? So it wants to know how you would prepare this solution if you had a 1 molar solution. So what we're going to be looking for is how much of the original we would use. How much volume of this 1 molar would be used. So we're going to be solving for V1. So we're going to arrange the equation to solve for that. So it'd be M2V2 over M1. Okay? So it'd be 0.39 molar. And in this case, because we're going to have molarity on the top and the bottom, molarity is going to cancel out. So we can actually leave our volume in milliliters. Okay? Because our molarities cancel out, so we can leave it in milliliters. And so we do that math, and we would get 189 milliliters. So the way that I would prepare this solution, and this is where a lot of kids get confused, is I would take 189 milliliters of my 1 molar solution, and I would add enough water to equal 485 milliliters. I wouldn't add 485 milliliters to it. I have to equal it. So I would actually add 296 milliliters of water to this right here for a total of 485. Okay? For a total of 485. I would never prepare a solution of 485 milliliters because that's a hard volume to, I would do 500. I don't know why they did 485 because of our flask and stuff. But that's how you would actually make it. So I want you to understand that you don't take 189 and add 485 to it because that's V2 is your final total volume that has V1 added in it. Okay? And we're not doing this. I think that's where we're stopping today. Yep, nope. Yep, that's where we're stopping today.